Assalamualaikum and hi. My name is Hamsyari Hamizan bin Zaidi, and today I would like to present our report for the assignment 2, which is conducted by Dr. Chua King Lee. Okay, before I start, I would like to introduce my group members. First is Hariz Raziq. Next is me, Hamsyari Hamizan. Next is Firdaus Azizi, Luqman Al Hakim, Nazrein Hakkeem bin Aziz. Okay, let's jump to the introduction. Before we go to the introduction, I would like to briefing first about our question and the problem statement. Okay, now we can see the figure 1 show block diagram of a temperature control system that develops using LPC 1768 microcontroller. The system employs a LM35 temperature sensor to continuously detect temperature of water in manufacturing plant. The LPC 1768 microcontroller is main controller unit to capture and convert the reading from the LM35 into equivalent analog voltage. In order to maintain the water temperature within a desired range, a heater and a cooler will be operated accordingly based on the reading that measured by the LM35. And we need to assume that desired water temperature is within the range from 55 Celsius to 80 Celsius. Okay, let's go to the introduction. So basically, in modern manufacturing processes, maintaining optimal temperature condition of water is crucial for ensuring the quality and efficiency of various operations. So I can say that this project focuses on developing a temperature control system designed to monitor and regulate the temperature of water within a specific range, but need to use the LPC 1768 microcontroller and the LM35 temperature sensor. As we get the question that we need to primary objective of the system maintain the water temperature between 55 and 80, like the mentioned before. So ensuring that the processes dependent on the water temperature operates smoothly and efficiently. So we need to use the LM35 temperature sensor, as we know, as a precise and easy to interfacing, and it can provide continuous analog voltage reading proportional to the water temperature. So this reading can posed by the LPC 1768 microcontroller, which is a central control unit for the system. Okay, so the control logic is developed using the key microcontroller vision integrated development environment IDE, which offer tools for writing, compiling, and debugging code for the LPC 1768 microcontroller. So the program is written in C or C++ language, utilizing the IDE features to manage the microcontroller peripheral effectively. So basically, this report can describe the design, implementation, and functionality of the temperature control system, including the system architecture, component interactions, and control logic. So it can highlight the advantage of the using LPC 1768 microcontroller and LM35 sensor in industrial temperature control. Okay, next we go to the challenging if we use the kill apps, and the common issue and the solution. I have do the problem statement or the common issue, and I give the solution too. So first is code compilation. First is code compilation error. So the problem is compilation error from syntax mistake or incorrect configuration. So the solution, review the code for syntax error and ensure correct project settings. So next is verifiable configuration. The problem, incorrect verifiable configuration, like the ADC, can cause inaccurate readings or malfunction. So the solution, we can check the LPC 1768 datasheet and user manual for proper configuration parameters. Use example code from key library for guidance. Third is debugging and simulation. So the problem is debugging complex system interaction can be difficult. can be difficult. So the solution, we just use the key debugging tools such as breakpoint and step execution to monitor program flow and variable values. So we can simulate the system behavior using the integrated simulation environment before hardware deployment. So last but not least, the memory management. So the problem is inefficient memory usage can cause instability or crashes. So the solution, we can optimize the code for efficiency memory use, avoid the memory leaks, and use the key memory management tools to monitor usage. That's all for me. And next, I will pass to the Firdaus who continue the report. Thank you.
Hi, Assalamualaikum. My name is Muhammad Firdaus Azizi bin Razi. My metric number is CE210117. Okay, for today, I will present about the methodology of our assignment 2 for my group. Okay, this section outlined the step to develop the software for a temperature control system using the LPC1768 microcontroller and LM35 temperature sensor. The system is designed to continuously monitor the water temperature in a manufacturing plant and control a heater and cooler to maintain it within the desired range of 55 to 80 Celsius. Okay, the development process begin with setting up the kill project for the LPC1768 microcontroller. This involves configuring the target device and initializing the necessary peripheral, specifically the ADC and GPIO module. The ADC is configured to read the analog signal from the LM35 sensor, which then will send the output to a voltage linearly proportional to the temperature. This voltage is then converted to a digital value, which the microcontroller can process. Next, GPIO pin are set up to control the relays that switch the heater and cooler on and off. Okay, first thing first, we need to know from the methodology is the step how we want to solve the problem. So the first step is setting up the development environment, which are same as the assignment 1, which we have to set up the project, create a new project, and configure the project setting. But for this assignment 2, is a little bit different, where we have to initialize and configuration for the ADC configuration and also the GPIO configuration. First thing first, we need to initialize the ADC module to read the analog value from the LM35 sensor. And for the GPIO, we need to set up the GPIO pin for controlling the relay module that switch the heater and cooler on and off. After that, we need to read the temperature from LM35, which we have used the analog to digital conversion, where we have to write a function to read the ADC value from the LM35. And the fourth, we have to use the control logic implementation, where we want to develop the logic to maintain the temperature within the desired range. If the temperature is below 55, then we need to turn on the heater. If the temperature is above 80 Celsius, then we need to turn on the cooler. And after that, if the temperature is within the range, we need to turn off the both heater and cooler. Okay, now I will present about the flowchart that my group has made for this assignment 2. Okay, as you can see from the flowchart, first thing first, we need to start the program. And after that, it will initialize the ADC and GPIO pin. And after that, we have to read the ADC value from LM35. After we have read the ADC value, we need to convert the ADC value to the temperature, which the program will read the temperature. So as you can see here, if the temperature is below 55, we will turn on the heater. And if the temperature is over 88 Celsius, we will turn on the cooler. And after that, if the temperature is between the 55 and 88 Celsius, we will turn off the heater and cooler to maintain the temperature. And then it will go to the end. Okay, that's all from me. Now I will pass it to my next member to present about the result and analysis. Thank you.
Okay, as you can see here, this is the coding for our program. Now I will run the simulation for this program. Okay, as you can see here, GPIO2 is for our input, which is heater and cooler, and GPIO0 is for our interrupt, which is emergency switch. Now I will run the simulation. Okay, as you can see here, we will put the test for our heater. The heater need to be function in 55 degrees or below. Okay, now I will enter the value below 0.5, which is equivalent to below 55 degrees. Okay, now I will start. As you can see here, pin 7 turn on, which is the heater. Okay, now I will turn on the cooler, which need the value of 0.9, which is equivalent to higher than 80 degrees Celsius to be functioning. Okay, now as you can see here at pin 8, which is cooler, fully functioning because it turned on. Okay, now we will test our interrupt. First, we clear the logic analyzer. As you can see here, the interrupt, turn on the interrupt. And as you can see here, both pin 8 and 7 won't turn on because of interrupt. Here, okay. You can also see the result in this logic analyzer. Here, as you can see, the cooler should turn on, but when I turn on the interrupt switch, the cooler turn off. We try it for heater. Enter the value for heater. Okay, now, okay, as you can see here, the heater turn on, but when I turn on the interrupt, which is emergency switch, the heater turn off. Also, the range for 80 degrees and between 55 degrees should make both cooler and heater won't turn off. Okay, here as we can see, both pin 7 or pin 8 won't turn on because of the range of 55 degrees and 80 degrees should not have either cooler or heater turn on. Okay, thank you.
Hello, my name is Luqman Al Hakim bin Mohammed. My metric number is CE210045. Now I will discuss our project which focus on developing an effective temperature control system for manufacturing plants. We aim to maintain water temperature within the critical range of 55 degrees Celsius to 80 degrees Celsius. To achieve this, we use the LPC1768 microcontroller paired with the LM35 temperature sensor. The LM35 is known for its precision, providing continuous analog voltage reading directly proportional to the temperature. The LPC1768 microcontrollers analog to digital converter, or we call it as ADC, play a crucial role here. It converts this analog signal from the LM35 into digital data, which we then use to control a heater and a cooler. The control logic for the system was implemented using the Kale Microvision IDE. This software is integral to our project as it turns on the heater when the temperature drops below 55 degrees Celsius and activates the cooler when the temperature exceeds 80 degrees Celsius. Safety is paramount in our design, that's why we include an emergency kill switch. This feature ensures that both the heater and the cooler are turned off immediately in case of any faults, preventing any potential hazard. The development process involves several key steps, which is the first is setting up the ADC and GPIO module. These modules are essential for reading the sensor data and controlling the output device. Second is writing function to read ADC value. Accurate data is very critical for reliable temperature control. The third is converting ADC values to temperature. This step translates the digital data into meaningful temperature readings. The last is creating the control algorithm. This logic controls when to turn the heater or cooler on or off based on the temperature data. The K-Microvision IDE was particularly helpful in addressing common issues such as code errors, peripheral configuration, debugging, and memory management. Our successful implementation of this system highlights the reliability and efficiency of using the LPC1768 microcontroller and LM35 sensor for industrial temperature control. Through precise simulation, we confirm that the heater and cooler operates correctly within the specified temperature limits Additionally, the emergency kill switch effectively interrupt both devices when necessary, ensuring safe operation. In conclusion, this project demonstrates the practical application of microcontroller-based system in industrial automation. It provides a robust solution for managing water temperature in manufacturing environment, showcasing the potential of modern microcontroller technology in enhancing industrial process. Okay, that's all for discussion for this project. Thank you.
Okay, hello. My name is Nazrein. So I'm going to explain the last part of this project, the conclusion. The project successfully designed and implements an efficient temperature control system tailored for the manufacturing plant environment, with specific focus on maintaining water temperature with a critical range of 55 Celsius to 80 degrees Celsius. Central to this system is integration of the LPC 1768 microcontroller and the LM35 temperature sensor. The LM35 sensor provides accurate and continuous analog voltage input corresponding to the prevailing temperature conditions, facilitating precise monitoring. The LPC 1768 microcontroller equipped with an analog to digital converter, which is ADC, translate to analog signal into digital, enabling the control logic to make a real-time decision. Leveraging the KAI Microvision Integrated Development Environment (IDE), the control logic orchestrates the operation of a heater and a cooler, ensuring that the water temperature remains within the specific parameters. Specifically, the heater activates when the temperature falls below 55 degrees Celsius, while the cooler engages when it surpasses to 80 degrees Celsius. Okay, thereby maintaining optimal condition for the manufacturing process. The development process encompasses configuring both of ADC and the general input-output (GPIO), laying the foundation of seamless integration and operation. Overall, for this project, it represents a robust solution to a temperature control challenge in the manufacturing settings, combining advanced technology with a meticulous planning to ensure precision, efficiency, and safety. Okay, thank you very much.